These four devices are called flip-flops. Flip-flops are circuits that are able to latch their output in a specific state whenever a sequence of voltage is placed on its input. This sequence can either be low followed by high or high followed by low. If the sequence is from low to high, they are called positive edge flip-flops. And if the sequence is from high to low, they are called negative edge flip-flops. Now, don't worry if you didn't quite understand that. I will explain in greater detail later. The important thing to note is that when they are connected together, they can generate the sequence of code necessary to count in binary. That is this code over here. To understand flip-flops, let's dig a little deeper into digital electronics. As you know, digital electronics operate in two discrete voltage levels, high and low. These are the signals necessary for a flip-flop to operate. So let us take a look and see how we will design a circuit that can produce a digital signal on its output. The circuit on my left is called a pull-up resistor, and the circuit on my right is called a pull-down resistor. These two circuits can be seen in all digital circuits. A pull-up resistor circuit causes the output to be normally high and then go low whenever the button is pressed. A pull-down resistor circuit cause output to be normally low and then go high whenever the button is pressed. The way you can instantly tell the difference between the two is that the resistor in a pull-up circuit is connected directly to positive power, while in a pull-down circuit it is connected directly to ground. So this resistor is connected directly to positive power, and this logic indicator right now is saying high. Whenever the button is pressed, it will go low. And in the pull-down circuit, this logic indicator is normally seen low. And whenever the button is pressed, now it's seen high. So you are creating a digital signal here because you are using one wire to switch from high to low, which is actually called a pulse, or when you have a stream of them, which is just a bunch of high-low, then it's called a clock signal. If it wasn't for these pull-up and pull-down circuits, this is the way how it would have to be done. This pin goes to positive power, this pin goes to ground, and then we will use a single pole double throw switch to switch the output between either high or low, just like that. Now we're ready to take a look at flip-flops. This circuit to my left here is a flip-flop circuit in the simplest form. There are no pull-up resistors or pull-down resistors to switch the input from high to low or low to high, nothing like that. And the reason for that is, if you have not noticed by now, the simulator will present a low signal on a pin if it's simply disconnected from a positive power. So I do not need to physically put a ground to it. If I just leave the pin floating, it would be considered ground. Now in the real world, when you're designing your circuits, you must put the pin to negative or ground for you to see low. You will not see low and your circuit will not work. You cannot leave the pin floating and it's considered low. It don't work like that. Okay, so for the sake of simplicity here, nothing clutter up my circuit, so I could explain flip-flops. There's, it's just the way it is. Okay, now the type of flip-flops that I will be using, and that's what I use in the rest of the counters, are called JK flip-flops. And for this flip-flop to work, the R input, K input, and J input needs to be high. And as you see in the circuit, they're all connected to high. And everywhere you see them in the circuit, it's going to be like that. They're all going to connect to high. Now, a flip-flop, as mentioned earlier, is a circuit that whenever it receives a sequence of voltage on the input, either from low to high or high to low, it will change the output to a state, and it latches that output in that state. Until you make that same signal again, the output will switch back to the previous state. It's better for me to experiment to enforce what I just said. For example, this circuit right now, this pin is low. Whenever I push this button, it will go high. Just like that. And notice that this pin down here was high. So it pretty much swap places. If I press it again, I go back. So it's a toggle effect. So it's just a toggle, basically. Every time you pulse, it just go back and forth. On, off. Off, on. Off, on. Depending on how you look at it. So basically every time you toggle, it changes state. Now, if you carefully look at this flip-flop, it is a positive edge flip-flop, so it reacts from a low to high. So the signal on this input, which is called the clock input, and the way how you can know the clock input in any circuit is that it has this little arrow on it. So anytime you see this little arrow, that is the clock input. And when it's a positive edge, it will look just like this. However, if it's a negative edge, it will have a bubble, just like this little tiny bubble here would be on the, right here. Right? So let me start over again. If you take a close look, right now the clock input is seeing low. As I said before, even though it's not connected to ground, the simulator is considering it to be low. So it's seeing low right now. Whenever I press the button, it will go high. Now this flip-flop will react because now it's low and then the input goes high. Just like that. Now, had it been the other way around, where this input is normally high and then I go low, nothing would happen. Okay, and to prove that, I would have to actually modify the circuit so I could switch and have a normally high input. Okay, I've changed the circuit to prove the point. I changed the switch to a normally closed switch so we could have normally high going to the clock input. So right here, the input is normally high. So now the input is high. When we break the switch, it will go low. And you have to pay close attention and see that the flip-flop is not going to react. The moment the switch is broken, nothing is going to happen because it went from high to low. However, when I let go of the switch, because when I break the switch it becomes low, and then when I release the switch it becomes high, then it's going to react. So take a look at it. Nothing happened, right? Because I just went from high to low. So it didn't react. So the output did not change. However, the minute I let go of the switch, because now it's currently low, the moment I let go of the switch, it's going to be high. That's when it's going to react. See that? So that's what I mean by, when they react from high to low or low to high. And this may not make sense right now, but it's because of this why flip-flops are able to count. So if you have a positive edge flip-flop, you would use a pull-down circuit, and if you have a negative edge flip-flop, you would use a pull-up circuit. I will show you why the term positive edge and negative edge is used instead of pull-up flip-flop and pull-down flip-flop. This is called a clock signal. It is nothing more than a sequence of voltage. This is low, this is high, this is low, this is high. So every valley is a low and every mountain is a high. So when they say that the flip-flop react from low to high and they called it a positive edge, It's because the flip-flop react on the rising edge of the signal. See these green bars? They are the rising edge. So it's on the positive edge of the signal. That's when the flip-flop react. So that's why it's called a positive edge. Now if the flip-flop had react when it's going from high to low, then that would be in the falling edge. And then they would call this negative edge. Because they say when you're going down is negative, when you're going up is positive. So that's the reason why they use the term positive edge to mean low to high, and negative edge to mean high to low.